Boris represents today. So we have Lars Nolting from Aachen University. So Lars is there. Hi, Lars. We'll then have Schnaars from the University of Hamburg. Hi, Philippe. We'll then have Yuwei Weng from Tsinghua University in Beijing, with this beautiful view on the park of the university, I presume. And then Mara Hammerle from the Australian National University. So that's the four panelists we will listen today. And I suggest we change the order of the presentations to take into account the fact that some of our speakers today comes from the east part of the world. And for them, it's not the late evening, but the beginning of the night. So it's the case for Mara and Yuwei. So it's not a gender issue, Lars and Philippe, but it's just a question of the time zone. So we start with Mara. She's located in Australia, and it's really the middle of the night for Mara. So as yesterday, all our speakers have 20 minutes to present their work, and then we'll have some time, about a few minutes to discuss and ask questions to them. So Mara, if you are ready, and I guess you are, it's your time now.
Yeah, okay. So I'll just share my screen. You can see that, right?
Yes, we can see your slides now.
Okay. Yeah, so I'm doing, if it's okay, can you give me like a 2-minute warning or something like that?
Like how many minutes left?
Like a 2-minute warning?
Okay. 20 minutes.
Yeah, exactly.
20 minutes to present, Mara.
Yeah, exactly. Cool. But then like, okay. So I'm doing like my first paper of my thesis, which is on solar PV and energy poverty in Australia's low-income and low-wealth households. So it's the first paper of my thesis, which basically looks at vulnerable households and Australia's energy transition. Just as an overview, what I'm going to be talking about is a very basic kind of like paper presentation, so literature review and motivation, methodology, results, and the conclusion. The motivation kind of for my paper is the fact that many countries focus on energy efficiency policies to help households get out of energy poverty. So for example, in Australia, we had the low income energy efficiency program, which provided grants to governments, businesses, and community organizations. In the UK, there's Warmfront, which I've heard of. However, another potential opportunity in sunny climates is to focus on rooftop solar. So for example, in Australia, around 28% of dwellings have solar PV. We're one of the world's leaders in the uptake of solar PV, given that we have many opportunities, obviously, for solar PV in the form of solar exposure. And this is a bar chart over here, just comparing the low income and low wealth Australians in energy poverty by solar. So what we can see here is the percent of households in energy poverty, like the fact that the solar households have lower experience of energy poverty than the non-solar households. I'm focusing on the term energy poverty, basically to align my work with other studies in Australia of energy poverty. I realize that there's fuel poverty is used more in the UK context, and that's used more for heating. Whereas in contrast, many parts of Australia rely less on heating and use more energy for other energy services, such as cooking or cooling as well. So this is the number of Australians in energy poverty, comparing the objective versus the subjective. Subjective, for anyone who doesn't know, is simply just talking about the feeling of being in energy poverty, so like perceptions of energy poverty, whereas objective is talking about kind of comparing incomes and energy expenditures. And this is the percentage of all Australians in energy poverty. So a natural question, obviously, is who are these households? So generally, when we're thinking about these households, at least for Australia, we're thinking about remote communities. So for example, Aboriginal and Indigenous communities, families with children, or like households with children, members with disabilities and or long-term illness, and English language difficulties. Determinants of energy poverty from the literature is low incomes, social welfare status, so like low social welfare status, low levels of wealth, low education, and unemployed. Low income and or low wealth households are more likely to experience energy poverty. In Australia, there are targeted policies for these households. So for example, in the state of Victoria, which is in the country's south, there's a policy for like based on incomes for under, which sounds probably quite high, but for under Australian $180,000 combined for the household. In the state of Australian Capital Territory, there's a policy for pensioners. And so a question from that is, to what extent does solar PV help alleviate energy poverty for these households? In particular, I'm looking at two research questions. So are low income and low wealth Australian households with solar PV less likely to experience energy poverty? And the second one is, do the impacts vary for different types of energy poverty? Theoretically, how can we get from like solar PV to a change in energy poverty? There are two types of kind of meters that we use in Australia. The most common one is if households have net meters. So what that means is that they first consume the electricity from their rooftop solar, and then any residual electricity is exported to the grid. So what happens there is that households with net meters consume their own solar output. Then we can have, well, that will reduce the amount of energy expenditures from the grid. And they will also get income from any residual electricity exported to the grid. As a result of that, households may increase their use of heating, for example, and or find it easier to pay their utility bills. The other type is gross metering, which is simply that the households will not consume any of the electricity from their grid and all of it is exported. And in that case, there'll be an increase in income. For my work, I'm looking at 5 dependent variables, and I'll get into that, what that means. The treatment variable, the main treatment variable is solar PV capacity, which is measured in kilowatts. I'm using data from a large nationally representative cross-sectional household survey, which is the Australian Bureau of Statistics 2015 to 16 Household Expenditure Survey and the Survey of Income and Housing. While it might have been nice to use more recent data, that's the most recent data set in Australia that we have that combines both energy expenditures and kind of feelings around financial stress, which is in the Household Expenditure Survey, and income and solar PV presence, I guess, which is in the Survey of Income and Housing. I use OLS and low-jet regressions, entropy balancing, and instrumental variable approaches. I'm not going to present the entropy balancing results at all. I'll just focus on the other two. And this is the main estimating equation. So we have SH, which is the solar PV capacity, a vector of covariates, the error term obviously, and this is the dependent variables. So what are the dependent variables? First of all, we'll get into well, the definition of low income and low wealth. So I'm looking at the lowest 3 deciles for either income or net wealth. Income, I'm defining as disposable income minus housing costs divided by what I refer to as the OECD factor. I look into housing costs, or adjust for housing costs, just given the amount of variation in housing costs across the country, so which obviously impacts on purchasing power. The OECD factor refers to the modified OECD equivalent scale, which is 1 for the first household, 0.5, for the first adult in the household, 0.5 for every other adult in the household, and 0.3 for every child. For the wealth, I'm looking at net wealth, which is assets minus liabilities, and that's just the unadjusted ABS variable, or like from the data set, and I divide that by the OECD factor. Same as before, so same definition. And over here, what we can see is the percentage of households with solar, and immediately what becomes obvious is that the total households, so that's like all of the households in the data set, that's a much higher percentage than either the low income households and the low wealth households. One caveat with this research is that the low income households could of course also be households with high levels of wealth, whereas the low wealth households could, be young high income families. Unfortunately, at this time, it's not possible to kind of distinguish or like to look at both low income and low wealth, given the low number of households. So kind of a first starting step is to look at low income and low wealth separately. The measures of energy poverty, the 10% rule, which is just the kind of slightly adjusted Boardman 1991 rule, which is simply dividing energy expenditures by disposable income. You can see that the disposable income, I've adjusted that by the OECD factor, which is the same as before. The energy expenditures is divided by the low income high cost factor. And all of this has to be greater than 10%. So what is the low income high cost factor? That's simply what, so Hills in 2012 was saying that there should be less variation in how we adjust energy expenditures rather than how we adjust disposable income, given the fact that members of the same household can share the same energy services. So for example, they can share the same lighting in a room. So this is basically just gives less variation, is adjusting for the household composition, but it's less variation than the OECD factor. I'm also using the low income high cost rule by Hills in 2012, which is the disposable income minus housing costs, the OECD divided by the OECD factor. So this like residual income minus the energy expenditures, which again I've adjusted, which is less than basically like the income minus energy expenditures should be less than the poverty line. So this is just the 60% of median kind of adjusted income. Plus, they also need to have energy expenditures above the median. So these are my two objective measures of energy poverty. My two subjective measures of energy poverty are indicator one is, does the household face financial difficulties preventing them from paying utility bills on time? And this is, the motivation for that is basically that households with solar PV, a lot of them install them because of the high costs of energy. Utility bills covers electricity, gas, and telephone bills. But given the fact that electricity and gas is more expensive than the telephone bills, and also that electricity and gas is kind of a main sticking point for Australian households, with, I would believe that the emphasis would be more on those expenditures. Indicator two is, does the household feel they're unable to heat their home adequately because of a shortage of money? And that's simply like saying, well, the reason for including that is because solar PV also generates electricity during winter when households need to heat their home. Okay, so moving on to the results. The main results for the low income households, these are the main results. One thing to note is the fact that you can see like the number of observations for the 10% rule and the unable to heat home are slightly lower. For the 10% rule, the reason for that is because of some like multicollinearity between the observations. The unable to heat home is because we needed to get rid of, I needed to get rid of the state of Northern Territory, because all of the households in the Northern Territory, it's up in the country's north, and heating is definitely much less of a concern there because it's hot most of the year, or quite hot most of the year. Okay, so what are the main results? The main results kind of show us that for both the weekly energy expenditures and for the objective energy poverty indicators, there's a statistically significant decrease. However, for the subjective indicators, there's no statistically significant impact. For the weekly energy expenditures, for example, a 1 kilowatt increase in the solar PV system size decreases weekly expenditures, or predicts a decrease in weekly expenditures by about $2.80. For the 10% rule, we can interpret that as a 1 unit increase in the solar PV system size leads to a probability, like predicts a probability or like a lower probability of experiencing the energy poverty as per the 10% rule by about 3 percentage points. I have included other covariates in all of these regressions, which include both household covariates or household explanatory variables. So for example, the number of people in the household, the age and the gender of the household respondent, and also dwelling characteristics. So for example, I merged this data set with data on solar exposure and the number of cooling degree days in a household's postcode, so in a household's like postal area. And I did that using geographic information systems. And it's also including like the type of dwelling, for example. Okay, so the main results for low wealth, on the other hand, are quite similar. So you can see that particularly for the 10% rule in the low income, high cost, there's about the same magnitude change. Again, there's a statistically significant impact for both the weekly energy expenditures and the objective energy poverty indicators, but no statistically significant impact for the subjective energy poverty indicators. So yeah, these are kind of the one thing that I might have, that I maybe should have mentioned is the fact that for the weekly energy expenditures, I'm using OLS for that, whereas for these indicator variables, they're binary variables, so I'm using LOJET and I'm presenting average marginal effects, is what you see in the tables. However, there might be problems with omitted variable bias. So for example, although I control for such things as net wealth, which probably does explain quite a bit of the variation, there could be omitted variables such as environmental sentiment that are also driving both whether a household has solar PV and also their energy expenditures, and therefore kind of flowing on to the energy poverty indicators. And there could also be a reverse causality. So for example, as I mentioned before, energy bills are a main point for why a household might want to install solar PV. So the instrument that I used in the paper is the average monthly solar exposure per square meter in a household's SA4. And that's quite a large kind of geographical region. So on average, it contains about 100,000 people between July 2015 and June 2016. There could be a need to kind of control for some variables to make sure that the exclusion restriction is okay. In particular, there's a need to control for temperature. So temperature is correlated with solar exposure, but temperature also impacts, for example, ability to heat a home. And so the main control is the average yearly number of cooling degree days in an SA4. The instrumental variable results, these are them. So we can see, for example, that the F statistic is greater than the threshold of 10. For these results, the number of observations is higher because I'm pooling both low income and low wealth households, the same as before, or like the same definitions as before. The first stage coefficient is positive, which is what we expect, because a higher solar exposure basically means that they'll be able to get kind of more, I'm thinking of a very Australian colloquial term here, but more kind of, yeah, more for their expenditure on their solar PV. Okay, and one other thing that I've controlled for is log wealth. So you could, for example, think that households with greater purchasing power are going to be able to live in more attractive areas. So, which is the reason why I'm including log wealth. I've also been thinking about including stuff like log income, which is also going to adjust for the differences in purchasing power. And the ability to kind of choose where you want to live more easily. what we can notice from these impacts is that they kind of tell a similar story to the OLS and LOJIT results in terms of the statistical significance. So there's strongly statistically significant impacts for the weekly energy expenditures and the objective energy poverty indicators, but less so for the subjective energy poverty indicators. However, one problem with this is that the magnitudes are probably a bit larger than what one might expect. So for example, the weekly energy expenditures is about -15, the point estimate. And a household on average has about a 3 kilowatt system, and also has energy expenditures, average energy expenditures of about $40. So yeah, it does seem that these estimates are a bit overestimated, because this would be kind of equate to a -$45 change in the energy expenditures.
Just a reminder, you still have 2 minutes left.
Easy, cool, thanks. Okay, so what we find is that solar PV is effective at reducing energy expenditures and experiences of objective measures of energy poverty. Solar PV, however, is less effective at reducing experiences of subjective measures of energy poverty. And that might be simply because there's for the subjective measures of energy poverty, there might be less people or less households kind of bunched near the kind of 0-1 cutoff for these variables. What I've done here with this bar chart is simply compared the change in weekly energy expenditures from the OLS results, and that's about a $3 decrease, with a study from the ACCC, so the Australian Consumer, sorry. I don't have it here, but the Australian Competition Consumer Commission, I'm probably getting that wrong a little bit, but yeah. And we can see that it's, I have adjusted for inflation, but we can see that it's slightly less. And that might simply be that my estimate is slightly less, and that might just simply be because of a slightly smaller system size for the low income and or low wealth households. So in conclusion, the uptake of solar PV is expected to continue to increase in Australia and worldwide. It's essential that policies are developed to ensure that low income and or low wealth households, as well as other types of potentially vulnerable households, are also able to participate in the energy transition. Without such policies, there is a danger for increasing levels of microgeneration possibilities to exacerbate existing inequalities. Okay. So yeah, thank you for listening. And that's what my website there, yeah. Okay, thank you.
Thank you so much, Mara, and congratulations for taking up the challenge of presenting in the middle of the night. So I can see that Lars has already a question. So Lars, the floor is yours.
Sorry, I was just clapping.
Okay.
What's your question then?
You have to ask a question now, Lars. I joke. Is everyone have a question, maybe? The audience?
I have one question, but actually, I think I cannot share my screen right now. This
okay, don't worry, Madeleine, you are free to ask your question.
Cool, great, thank you. Yeah, I think maybe the host can unlock my screen and also. Yeah, cool. Okay, great. Perfect, cool. Yeah, I have actually two background questions, Mark. I was
nice to see you again, by the way.
Yeah, actually agree. Good to see you again. I was wondering, can you say a bit about how these energy poor households actually finance these solar PVs? Because I guess it's not possible for them to finance these out of pocket. So are there some sort of financing schemes? And related to that, given that they're energy poor, are there some social welfare systems who could cover part of their energy expenditures? So for example, in Germany, social welfare programs cover heating costs. So I was wondering, how is that in Australia?
So there's a there's a big subsidy that houses were able to get called the small as part of the small scale renewable energy scheme, and that's basically an upfront subsidy that covers. It depends, like the amount of the subsidy depends on the solar exposure of the area. So higher solar exposure areas got a higher amount of the subsidy. And it covers about, in some cases, like about 50% of the cost. And so the other part would have been self-financed, or like financed through some means, like maybe a loan or something like that. But yeah, that does cover quite a bit of the upfront cost. And it's still like it's something that's continuing today as well. And in terms of energy expenditures, if you're like classified as like a vulnerable household and kind of meet some means testing, based I think predominantly on income, you're able to get like help with energy bills, but it's not necessarily like it's not like tied to heating, because obviously heating is kind of less of an issue here than in Europe. Yeah.
Maybe just a question, Mara, an additional question. All the PV holders in your data are under self-consumption scheme, or someone could directly inject all the electricity into the grid?
Do you mean like how do?
In Europe, for instance, we have different ways to develop PV, and a PV holder can either self-consume his electricity and inject into the grid what he do not consume, or he can, on the other side, choose to inject all his production into the grid. So, yeah. we do not have, I suppose we do not have more net metering in Europe. So that's the two questions I have. Is it an option to have net metering in Australia, and all your PV holders in your data are self-consuming the electricity, or some part of it could are under a scheme of full injection?
So there are both households, like we have both net metering and gross metering in Australia. So net metering is where you, like, I think that the definitions, from my understanding, differ slightly across countries. But for net metering, like how we view it is that you the households consume the electricity, and then residual electricity is exported to the grid. And you can get a feed-in tariff for exporting electricity to the grid. For gross metering, all of the electricity is exported to the grid. But that's not determined by the household. There were a few kind of state policies at the beginning when solar PV, when state governments tried to roll out solar PV and incentivize the uptake of solar PV, there are a few policies that focused on gross metering, but since then most households will have, or like all households will have net metering.
Okay, because
it was unfortunately not possible.
Yes, it could impact your the way you modelize your electricity consumer, because if you are under gross metering, it's not totally the same thing that if you are the net metering, the impact on your bill is not totally the same.
Yeah. So one way that I'm looking into that is by, like, unfortunately, the data set doesn't say, this is a net metering household versus this is a gross metering household. But one thing that I am doing, wasn't in my paper, but I am putting that in there, is doing kind of a sub-analysis based by state. So some households in the ACT, in the Australian Capital Territory, and New South Wales are on gross meters. So what I've done is, like, a part of a heterogeneity analysis is to drop those households and to focus on the rest of the households and see whether the results change quite a bit. What I'm finding is that the results are a bit higher For the households, when I drop, or like for the results, when I drop the New South Wales and Australian Capital Territory households, but there isn't that much of a change either. Like the results are still quite similar. Yeah.
Okay, so thanks for sharing this update of your results with us. I have a question, but I will leave you and spend a nice night. I don't retain you more. Enjoy your night, Mara. Thanks again for being with us despite this late time for you. And now I will give the floor to Yuwei, for which is becoming lately also. So Yuwei,
Yeah, here.
Let me talk about the climate neutrality strategy in China.
Yes, thank you. Thank you for changing my order. Yeah. Let me share the screen. I think you can hear. Yeah.
Yes, we can see it.
Okay.
Thanks.
Okay, good. Hello, everyone. I'm Yuwei from Tsinghua University. It's really my great pleasure to be here in this session for the best student paper. And my research topic is evaluating the use of negative emission technologies under China's carbon neutral targets for 2060. And this is the outline of my presentation. First, I will introduce some background of this study and then show the methods I used and some results. Finally, I will give some discussions. We know that BECCS and afforestation are two promising negative emission technologies. BECCS means bioenergy with carbon capture and storage. As a negative emission technology for achieving tough climate targets, it was first introduced in the article Managing the Climate Risk in 2001. And this is a schematic of BECCS. First, biomass plants can remove the carbon dioxide from the atmosphere through photosynthesis. And then the production processes of bioenergy would emit CO2. Then these emissions can be captured by CCS technology. So that in this case, BECCS can remove the CO2 from the atmosphere and provide energy at the same time. And we look here, this figure shows the medium scale of carbon dioxide removals in integrated assessment model scenarios under 1.5 degree. Most of the negative emissions are contributed by BECCS and afforestation. And also some previous studies show that by 2100, the average CO2 removals would be reach about 12 gigaton per year by BECCS and 4 gigaton per year by afforestation in global below 2 degree scenarios. And in September last year, China announced to scale up its INDC under the Paris Agreement by adopting more vigorous policies and more measures, and will reach carbon neutral before 2016 and ensure its carbon emissions peak in the next decade. However, there are many challenges for this largest carbon emitter in the world. China now only has 13 years from carbon peak to carbon neutrality, and from about 10 gigaton CO2 per year to net zero emissions. So in this context, since BECCS and afforestation can offset emissions from sectors which are very difficult or too costly to reduce, so they might play important roles in China's mitigation pathways to carbon neutral. However, we know that from modeled words to reality, now only relatively small investments are being made in NETs. Currently, there are only about 10 operating BECCS plants worldwide and capturing 2.4 gigaton CO2 per year. Yeah, and besides, concerns has also been raised about the feasibility and sustainable implications of large-scale NET deployment. As mentioned in the IPCC report, increased biomass production and use has the potential to increase pressure on water and land, food productivity, biodiversity, and so on. So therefore, it's very urgently needed to refine the deployment scale of NETs and to determine their political priorities. Now, let's review some literature. This table shows the overview of existing BAC studies. We can find that at the global level, the potential deployment scales of BACs and under ambitious climate targets and their social, economic, and environmental implications have been widely discussed. But these global studies have weaknesses in detailed consideration of the heterogeneous nature or socioeconomic conditions of each country or region. So they can't substitute local assessment to support policy making. While we can see here, at national and regional level, most studies only focus on near-term targets like INDC, and the potential economic implications and the environmental implications haven't been fully investigated. Here I list the 4 modeling approaches which are often used in NET studies. The first one is IAEE models. It integrates various systems into one modeling framework based on lots of assumptions. And the second one is bottom-up models. It can give detailed insights of specific technical aspects, but it can't capture direct or induced effects outside its boundaries. The third one is partial equilibrium models. This model usually gives more details about regional and sectoral aspects, but it doesn't consider macroeconomic balances and the impacts on sectors is not modeled. And here's the last one is CG model. With the broad coverage of economic and activities, it has strengths in capturing comprehensive economic interactions among sectors and individuals, as well as direct and indirect implications. So each model has its strengths and limitations. And I want to focus on the CG model in this study. So further, I reviewed some CG model studies. We can see that previous studies have made some attempts to integrate BACs and afforestation into CG framework. This table presents some modeling details. We can find that most of them are global scale studies, and they usually analyze the BACs and afforestation separately. While besides the coverage of biomass and bioenergy types are also need to be further improved. So here I summarize some research gaps in existing studies. The first one is about research area. At the national or regional level, the demand scale and the potential implications of BACs haven't been fully investigated. Second, most previous studies analyze the BACs and afforestation separately, so their combined effects haven't been discussed. The last one is for the methods. Both economic interactions and complex technical details of NETs bring challenges for traditional top-down or bottom-up models. To fill the aforementioned gaps, I aim to evaluate the use of NETs, here means BACs and afforestation in China's decarbonization pathways towards carbon neutrality. Specifically, I wrote the 3 sub-questions The first one is what is the scale of BECCS and afforestation in mitigation pathways towards carbon neutrality? The second one is what are the biomass types and their proportions for the feedstocks required by BECCS? The last one is what are the macroeconomic implications and the land use consequence of an NET deployment? Now let's look at the methodology. My study builds on a dynamic recursive national CEST model designed for energy-related research. It's called CHAIR-BE. As an extension of the CHAIR model developed by my research group, CHAIR-BE is improved in 3 aspects. First, it's splitting subsectors from agriculture and bioenergy from the original aggregate sectors. Second one is modeling NETs, including bioelectricity, biofuels with CCS and afforestation. And also I have incorporated a land allocation model to simulate land use change. And this figure shows a core model structure. And here shows the sectors in the CG model. The original sectors are firstly aggregated into 23 broad sectors, including 5 energy sectors and 4 agriculture sectors and some other sectors. And further, refined oil, electricity, and the crop sector are further split into more detailed subsectors. This is the CES production structure for bioenergy and the BECCS production. The production process of bioenergy would emit CO2 through biomass conversion, and the factory has options to buy CO2 permits or for its emission, or to use the CCS technology to capture its emission. And this choice would be made based on the CO2 price and the cost of CCS. So therefore, this production structure can supply and demand carbon permits simultaneously. And if permit supply equals permit demand, it's considered carbon neutral. If permit supply is greater than permit demand, it's considered carbon negative. Now let's have a look at the land allocation module. Considering the land heterogeneity, here the total land factor is split into sub-accounts in the CGE model. So here the total land endowments can be allocated across alternative uses in response to the change of the land rents. And since afforestation can provide negative emissions, so here carbon permits are modeled as a byproduct of afforestation here. Okay, now let's move on to the scenarios. 4 scenarios are designed. In the reference scenario, no carbon constraints is applied. And in the 2 carbon neutral scenario, assume that China's carbon emissions would peak in 2025, and then it would reduce and achieve net zero emission by 2060 with a carbon budget of about 220 gigatons CO2. The difference between these 2 scenarios is that only BECCS can be used in scenario 3, while afforestation can also contribute to negative emissions in scenario 4. And here, scenario 2 holds the same carbon peak time and carbon budget with 2 carbon neutral scenarios, but it would reach only near zero, but not net zero by 2016, because no NETs can be applied in scenario 2. Now let's move on to the results. From these figures, we can see that in scenario 3 and 4, the cumulative CO2 removal by NETs from 2018 and to 2016 will be about 30 gigaton and 37 gigaton respectively. And with the cost of BECCS decreases and the carbon price increases over time, BECCS would be more cost-effective than afforestation. So its share would be larger than that of afforestation. And also in 2016, about 73% of the negative emissions are contributed by bioelectricity with CCS. This figure shows the electricity generation by sources in different scenarios. In 3 decarbonization scenarios, fossil-based electricity will tend to phase out, and more renewable energy and nuclear energy would be applied, about more than 80%. And in 2060, the shares of bioelectricity will be 28% and 26% in scenario 3 and 4, while this share will be only about 10% when it can't be combined with the CCS technology in scenario 2. Also, we find that limiting the use of NETs will accelerate the phase-out of fossil fuels and reduce the total power generation. Here, these figures show that refined oil production in different scenarios. Fossil fuels would dominate in the reference scenario, while in other scenarios, their shares would fall to about 30 to 50% by 2060. And in carbon neutral scenarios, the proportion of biofuels would increase rapidly, reach about 60% and 50% by 2060. And also the first generation biofuel would keep a small share, while the share of the second generation biofuels will increase gradually. And the second generation biofuel with CCS would come into the market about 2030. Also, this is a feedstock structure for bioenergy production. We can see that the shares of cellulosic crops and residues would grow rapidly, especially after 2030. And the sugar crops would present a slow growth trend, and the share in 2060 is about 4 to 8%. While green crops will be reduced to a very little share. And the demand for total biomass in scenario 3 is nearly 20% higher than that in the scenario 4. So this table presents the GDP loss and the carbon prices in different scenarios. It can be found that if BECCS and afforestation are adopted as NETs, the negative impacts on GDP would be alleviated to some extent, and the carbon price would increase rapidly after 2040. In 2060, the carbon price in scenario 2 is the highest. Now let's move on to the discussion part. If the scale simulated in my CG model can be satisfied by the feedstocks, here I compare the bioenergy demand with the technical bioenergy potential in previous studies. You can see that in 2030 and 2040, the potential for bioelectricity could be satisfied by the demand, while the biofuel might face a feedstock shortage in deficit irrigation conditions, and both bioelectricity and biofuel would may not have enough bioenergy potential to meet its demand after 2040.
It's a 2-minute time left. warning. So you still have 2 minutes to go.
Okay, thank you. It also needs to be noted that when we considering economic and environmental constraints, the actual bioenergy potential will be even lower than the technical potential here. So the gap is still very large. And here I compare the amount of CO2 removal by bags and in this study with the results of other studies. As shown in this table, these studies have different sector coverage for bags, and under the ambitious climate targets, carbon removal by bags in 2050 is about 1 gigaton per year, and the cumulative CO2 removal will be about 10 gigaton. Yeah, and also we can see that there's still exists some difference among these results, but it's not very large. And in future, more comprehensive model intercomparisons and uncertainty analysis need to be conducted to improve the reality of this kind of assessment. Finally, the following conclusions can be drawn from this study. First, bags and afforestation could play important roles in China's mitigation pathways to realize carbon neutrality. Second, planting dedicated energy crops is essential for bioenergy and bags development, because nearly half of the feedstocks would consist of energy crops in 2016. And the last one is adopting bags and afforestation could reduce the mitigation costs and alleviate land use change. Here I summarize some contributions of my work. First, through the disaggregation of the aggregate sectors and incorporating some NET technologies, the CHAIR-B model can capture key low carbon technologies and NETs in detail, which breaks the highly aggregated feature of traditional CG models. And second, two promising NETs are integrated into the scene modeling framework, while previous studies usually analyzed them separately. So here their combined effects can be captured and compared with the standalone effects. And the third one is, as a national scale study, it can provide local insights to supplement the existing global studies and to help to refine the local actions and the policy makings. Also, I have listed some limitations of my work. First, the coverage of bioenergy types is limited. We know that other types of bioenergy like biogas, biodiesel, and biomass co-firing, etc., are also likely to be options for remove CO2 when in future. And second, regional environmental constraints are not taken into account in this study. Third, the settings of some of the model structure and the parameters and assumptions would bring uncertainties to the results. So in future, I could do some sensitivity analysis of the key assumptions or parameters. Okay, this is a main reference, and this ends my presentation, and thank you for your attention. I welcome your questions and comments. Thank you.
Thanks a lot, Yuwei. So now the floor is open to get some questions from the audience. I have some. First question I have, Yuwei, is what are the implicit CO2 costs that are associated with the different technologies that you develop in your scenario? What are the costs? Because you mentioned the extent of CO2 reduction from those technologies, but what are the costs associated with those technologies?
You mean the scenarios?
Yeah, what drive the choice of technologies in your model?
Sorry, maybe I didn't understand well of your question. Do you mean
How do
which?
you choose your technology in your model? How you favor one technology over the other one? You must have something which is the implicit CO2 cost of reducing emissions from using one technology or another.
Oh yeah, so in scenario 3 and 4, I modeled NET technologies in these two scenarios. And in scenario 3, only bags can be used. And in scenario 4, bags and forestation can be used. Yeah, and also like some solar PV or wind energy or nuclear energy, they can some traditional low carbon technologies they can use in all the scenarios. And yeah.
Okay. As I understand, the emissions trading scheme will play a strong role in the reaching of this climate neutrality goal in China.
You mean the actual deployment of this? Actually, in China now we don't have any bags plants. Yeah, we have some CCS instructions, and
but you mentioned the carbon market in your presentation and the possibility for producers, for industrial, to use carbon permits to be compliant with the CO2 constraints.
And you mean the constraints for these technologies, right? Oh yeah, my constraints is based on some previous studies, like they will do some potential analysis about how much biomass China can provide it in the future. So I use this as a constraints in my model. But since we didn't have actual plants, so some data are based on global studies. Yeah.
Okay, thanks a lot, Yuwei. Now we will turn to Lars. And Lars, maybe Madine, you have a question? Sorry.
You have just time for one more.
Yeah, we have 1 minute.
Okay, cool. Yeah, just briefly on the. I was wondering in how far your model accounts for changes in carbon emissions resulting from changes in land use due to the deployment of the bags. So if there are no more land use is used to plant biofuels or bioenergy, this means less land use can be used for farmland. Do you account that sort of decrease in emissions in your model? And also there might be a decrease in afforestation because no more land has to be used for this biofuels. I was wondering, how does your model account for these changes in emissions?
Oh, you mean that if we need to plant lots of energy crops, so we don't have enough land for food, you mean?
Yeah. Yeah, because then the emissions from food could decrease because maybe you done because maybe the emission, because you don't anymore have these emissions from livestock, and maybe you have to like deforest some trees or things like that to have more space.
Oh yeah, it's a good question. Actually, that here I have added the marginal land to my land allocation model, because if I don't add this marginal land and only use the existing land use types, my model can't get a feasible solutions for future large-scale bags deployment. Yeah, so when I add this marginal land, it can get the feasible solution. But here in China, the marginal land has many, different definitions. So the range, how much marginal land China will provide in future is not sure. Yeah. So I think this will bring some uncertainties. Yeah, but it helps me a lot for this model. Okay.
So this is sort of a residual, which is not yet used, but might.
Yeah, if we don't use marginal land, like land for wheat or corn and other greens, maybe use it to plant energy crops. Yeah. Thank you.
That's okay, Malin. So speaking about energy modeling, we are now giving the floor to Lars. We'll say some good insights on how to build a nice model with not so much complexity.
Thank you, Boris.
You're welcome.
Thank you.
Okay, thank you. I hope you can all see my screen now.
Yeah.
Okay, perfect. So a warm welcome from my side. My name is Lars Nolting, and I'm from RWTH Aachen University in Germany. And I'm very happy to give you a presentation today with the title The Guideline Through Complexity, Assessing the Security of Electricity Supply. And as has already been introduced, I'm focusing on how to build adequate models which are not too complex, but which can still cover the main features of energy systems. And as the field of application that I want to show today is the security of electricity supply, let me start with showing you some details about the current situation regarding the security of electricity supply in Central Europe and especially in Germany. What we can see here is the installed capacities in Germany, and as a dotted line, also the peak load, which might occur during a very cold year. And what we can see is that from 2011 until today, and also for forecast scenarios until 2025, the capacities have been increasing. So the green share here of the bars, which is the renewables, mainly wind and PV in Germany, this is really increasing, and also the overall installed capacities are also increasing. But if we have a look now at the secured feed-in, which is now shown, these are not the installed capacities, but the contributions of different power plant types during the peak load hour, we can see that this is in fact decreasing over the course of the time. And what we can see is that for future scenarios beginning from 2023 on, it's really close to the peak load that might occur during a cold year. And this means that assessing security of electricity supply is becoming more and more relevant in Central Europe and especially in Germany, due to the decommissioning of nuclear and fossil energies, which we are facing. And so it is really important to assess how the energy transition does affect security of supply. And this is a very important research question. So as energy scientists, if we want to answer a research question in the which affects the overall energy system, what we do is we build energy system models, because this is the only way that we can conduct experiments with the energy system. And if we have a look here at the left-hand side, we see this is a depiction of the energy system from a system theory point of view. And the right-hand side shows how now a model would work. It would take some parts of this model and try to depict the relation of an output vector from an input vector. And if we think of the energy system, what we can see is that there are different drivers for complexity in the system. One of these drivers is that there's a lot of different actors in the system. For example, this amount of actors is also increasing, for example, due to the expansion of distributed renewable energies. So we do not have a few big power plants, but we have a lot of distributed energy feed-in. Then another driver for complexity would be that we have networks in this system, meaning that the different subsystems are linked. For example, if we think about international electricity trade. And another driver for complexity would be the dynamics of the system, meaning that we have very frequent changes of the circumstances and of the states of the system, for example, due to regulatory changes. And then there are other drivers for complexity in the energy system, like path dependency, lock-in effects, and learning. So what we can conclude is that energy systems are complex systems. There's also a paper by Bale where they really show that there are a lot of drivers for complexity in the energy system. And what we can further conclude is that these drivers for complexity are increasing, and meaning that the complexity of the energy system is increasing, and also the complexity of the models to depict this system is increasing. So this leads us to the identified research gap, which I want to show in the next slide. And this is that a dedicated complexity management is needed in energy system analysis, but it's not implemented at this time. So what we want to ask is, what are the benefits and drawbacks of more complex models to provide policy relevant insights in the field of energy sciences? And how can an optimal level of detail for an energy system model be defined and reached? So we really want to assess this research gap and show how a complexity management might look like. And the security of electricity supply is a very interesting field of application here, because we need to depict the complex energy system, and we have a lot of urgent and relevant research questions in this field of application. To give some first insights on how an optimal level of detail could be derived, I want to introduce a general mathematical model. What we can see here is the maximization problem of the net benefit of a modeling approach, depending on the level of detail, the LOD, that is used in the model. So what we want to maximize is the benefits, which are shown here as beta, minus the cost C. And if we want to maximize this difference, what we need to reach is a point where the marginal benefits beta prime equal the marginal cost C prime. And in the graph, we can see that the benefits of a model increase by increasing the level of detail, but also the cost increase. And these benefits refer to the utility that I can gain from more detailed insights by using more detailed models. But the costs that need to be accounted for are, for example, that it takes longer to implement these models, that the model runtimes are longer, thus limiting the amount of scenarios that I can investigate. The interpretation of the results becomes more complex, and it might also be less easy to directly see or to directly anticipate the results of a model. So what we can see is that the benefits increase and the costs increase with the level of detail, but also we have the dotted lines in this left graph where we see that the marginal benefits decrease and the marginal costs increase, meaning that there is an optimum which is represented by the intersection of these two curves, which is the optimum level of detail. And this is the first key takeaway, which is that the optimal level of detail is not the maximum of the possible level of detail, but it's the point where the marginal benefits are equal to the marginal costs of increasing the level of detail of a model. And this is quite relevant because many modelers tend to make their models as complex as possible. And now to apply this mathematical framework a bit more and to make the result more tangible, I want to show two different modeling approaches for the field of security of electricity supply. One of them being deterministic length sheets, which is a very simple model where we can directly see the input data and the results of the model. So here on the left-hand side, we have the supply side of the energy system, where we can see the installed controllable capacities, the non-availabilities, the renewable feed-in, and all of this is summed up then to the power supply within the country under investigation, in this case Germany, and then we have the available imports. On the right-hand side, we have the demand side, where we have the peak load, then we have some system services, everything added up to the overall peak demand. And the difference between those two, this is the capacity margin that I have. And if it's if the total supply is higher than the total demand during peak load hour, we can see, okay, this the security of supply is not set at danger in this scenario. So this is a very top-down, straightforward approach to model security of supply. On the other hand, we have very complex models that can be used, like probabilistic simulation models, where we model the energy system in hourly resolution, representing the different system states. Here in the red curve, we show the availability distribution of power plants, so at which probability, which capacity will be available. And then the green line represents the residual load, which is the electric load minus renewable feed-in, and also accounting for imports. And from the intersection of these two curves, we can calculate the probability that a given load will be covered. And this is done in hourly resolution with very high modeling efforts to compute this availability distribution, and also usually for different weather situations. So this is not only done once, but 30 times for 30 different weather situations in future scenarios. So now we can see, okay, there are two different model approaches, and what we now want to do is to compare what results can I draw from these models. And to do so, we want to focus on a scenario for Germany for the year 2023, where we saw that it might the capacity margin might be quite low, and it might be really interesting to see if the security of supply is there in Germany or not. And here we have a scenario for the year 2023, where we see, okay, the total supply excesses the total demand. But if we have a look at the current plans in Germany, which are to phase out coal-fired power plants, and we implement these changes in the scenario and the investigation, we can see what happens directly in the model. We see that the amount of installed comparable capacity is reduced, and we can see how this directly affects the result of the calculation, meaning that during peak load hour, there might not be enough power supply to cover the power demand. So here it's really straightforward to see how results and input data are linked. These are the outcomes of the complex model on the other hand side. So here we see the two scenarios, 2023 and the 2023 scenario with a reduction of the installed capacities of coal-fired power plants. And these box plots represent the 30 different weather years that are used to simulate different weather situations for the future scenario. And we can see a quite similar picture that for 2023, everything is okay. We do not have any loss of load expectation. So there are no hours where, or at least there are almost no hours where it needs to be expected that the load cannot be covered. But for the other scenario, there are weather situations where we might have some loss of load. But here we can directly see that now it's really hard to see how these results are stemming from the input data. And this becomes even more severe if we have a look at the uncertainty of input data. And what we can see here is the changes in input data if we compare two different input data sets from the year 2017 and 2018 that have been published by NCOE, which is the Union of the European Transmission System Operators. And what we see here is that they changed the data regarding the installed capacities in Central European countries. And this led to a reduction of the import capacity that we have in Germany in peak load hour. And this happens quite frequently. These data sets are updated on a yearly basis, and they change by quite a lot. And if we now apply this to the models, what we find is that for the more simple model for the deterministic balance sheet, this is the old data that I showed before, and we can now directly see how the change in input data changes the results. So now the available imports are reduced from 7.6 gigawatt to 2.1 gigawatt. And this affects, of course, the delta between total supply and power demand. And you can directly see now why this data is changed and how the input data linearly affects the output of the model. This is quite different for the complex model, because there we have nonlinear reactions. What happens now to this model is that the import capacities are shifted on an hourly resolution, meaning that we have highly nonlinear effects of the input data on the outcome of the model. And this can be shown here. This is the old results that we have with this MAF 2017 data. MAF stands for Midterm Adequacy Forecast. These are the big reports that are published for Europe to assess the security of electricity supply. And if we now use the new data, we see that the box plot is jumping. So this is now, we have now really severe problems regarding the security of electricity supply in this scenario, because we have a mean expected loss of load duration of 2.6 hours for Germany, which is really high, because usually we have 0 hours. And if these are our model results and we would not have had a look at the deterministic balance sheets, it would be really hard for us to trace back this jump to the change in input data. And it's really hard to anticipate how the model reacts to changes in input data, especially if the results are really close to tipping point. And if we now summarize the findings and we compare the two modeling approaches, the deterministic balance sheet and the probabilistic simulation models, what we see is we have a direct visualization of input-output relation for the deterministic balance sheets. For the probabilistic simulation models, that is really hard to anticipate. How will the model react on changes in input data, especially regarding uncertain input data for future scenarios? We have the data requirements are really low for deterministic balance sheets. We only need to have the installed capacities and the renewable feed-in and the demand, and then we can directly take the difference between those, and that's all the data we need. For the probabilistic simulation model, we need a lot more data. We need to have hourly data. We need to have data for different weather situations, and we do not only need to have that for Germany, but for whole Central Europe to assess the security of electricity supply. And the interpretation of the results is rather straightforward for the deterministic balance sheets. There we could directly see the difference between supply and demand, is it positive or negative. So this is a very good estimate to see, will there be sufficient supply during peak load hour or not. For the probabilistic simulation models, the outcomes are, for example, box plots or distribution functions of the loss of load expectation. And there are some statistical capabilities are needed to interpret and to understand these results. And if we now want to use these results to give advice for policymakers, for example, it's really hard to show the main outcomes of the very complex models using only the statistical capabilities that can be granted. Also, if we have a look at the possible number of scenarios, this is almost unlimited for the deterministic balance sheet, because it's really easy to use this model over and over again. We can see if we change the input data, how does this affect the result? And we can do that as often as we want to. For the probabilistic simulation models, each model run for a scenario year takes about 10 hours, because it's really computationally complex to calculate this distribution function of the availabilities. So the number of scenarios that can be investigated is rather low. And the benefit of probabilistic simulation models is, of course, that there are less severe implicit assumptions, because we do not only focus on the peak load hour, but depict all hours of the system. So the level of detail of the modeling approach is higher. But what we can conclude here is what I would call the complexity dilemma, meaning that more complex models require more uncertain input data, and they limit the amount of possible scenarios that can be investigated in future scenarios. Meaning that if I want to have very detailed information about future scenarios, I need to use very complex simulation models, but I need to keep in mind that these models also come with high uncertainties regarding input data, and thus regarding their results.
Lars, you still have 2 minutes.
Thank you. And so now what I would suggest to reach this optimal level of detail is a 3-step approach. And the first step would be to determine the additional benefits by increasing the level of detail. So what further insights do I get from increasing the level of detail? Then I need to account for the additional costs that are associated with increasing the level of detail. Maybe I can only investigate a limited number of scenarios if I have a very, or if I increase the complexity of my model approach. And then from these two combined, it can be the optimal model choice can be determined that reflects both the preferences of the modeler and of the interpreter of the results and the cost structure behind the model. And so what we as modelers need to do is to keep in mind the two sides of parsimony, meaning models should be as sparse as possible, and the call for complexity by Sterling, meaning that we cannot oversimplify things. And this can be done by using these 3 steps to really determine the optimal level of detail for modeling approach. And to conclude, I want to summarize the main findings of today's presentation. The first one was to provide a mathematical framework which showed that the more complex model is not superior per se, but there is an optimal point for the level of detail that should be used. Then we introduced the complexity dilemma that showed that more complex models require more uncertain input data, and thus it's really hard to give very detailed insights for future scenarios with a high level of uncertain input data. And we introduced these 3 steps for modelers that can be used to find and reach the optimal level of detail for the model approach. And so as a key takeaway, I would say that accounting for uncertainties is more important than depicting all details of the energy system, in particular for future scenarios. So rather than taking the most complex model that is possible and only being able to calculate 1, 2, or 3 scenarios, it's better to decrease the level of complexity of the model, but be able to show the uncertainties of the input data and how they affect the model outcomes. And with that, I want to thank you for your attention, and I'm happy to hear your questions and comments.
Thank you very much, Lars, for your presentations. It is nice sometimes, you know, to step back and think about what we are doing. And I think you did the job. It's good lessons to model energy system and to try to be more accurate when you do this task. So maybe questions? Yes, from Richard. I don't know who is Richard. Hi, Richard.
Sorry, Richard Green from Imperial College.
So
thanks very much. It's interesting stuff, and you know, a huge dilemma. You know, what goes in and what doesn't. I think sort of sometimes putting lots and lots and lots of things in is the worry that you leave out something that turns to be important. Mm-hmm. And there's a wonderful radio clip. It's probably about 10 minutes into a half-hour program, and I'll put the reference. I've just checked the web link. I think it works all over the world. It's a BBC program where somebody was talking about what to put into a model and what to leave out. So I'll just put that reference in. But yeah, interesting presentation. So thanks.
Yeah, thank you. That's very good advice. Yeah.
Maybe another question. We have still some times to. I guess the degree of complexity also depends not only on the accuracy of your model, but also on your strategy. If you want to publish in a good journal, maybe you will move to a more sophisticated model. But if your goal is to advise policymakers and to represent more simple way the reality and the complexity of the energy system, maybe you will prefer to move to a more simple model. I guess.
Yeah. Yeah, exactly. That's what I meant by that the costs and the preference also depend on the audience of the results. So depending on who you're showing your results to, there are some statistical knowledge, for example, that you can presume that scientists have, that politicians sometimes don't have, and then it's really hard to explain the results. Yeah.
Yeah, I agree, and I'm not sure about the more sophisticated model are the best one to explain to a policymaker what is the right decision to and the right step to to make. And usually the most simple is the model, and the better it is to disseminate your research to large audience. But this is the life of a researcher, sadly. Thanks a lot, Lars. And we'll move now to our last speaker, which is Philippe. So Philippe is here also. Philippe, the floor is yours for 20 minutes as well.
Thank you. Okay, hi and welcome.
And Richard share the links to the BBC report in the chat room. Thanks,
Great.
Philippe. Sorry.
Yeah, no worries. Okay, yeah, hi and welcome. I'm Philip. I work at the University of Hamburg, and I'm going to present you my research on renewable risk and its impact on market prices. And to analyze this, I use data from Germany, so hence the subtitle. Let me just put my spotlight on. I need this later. Okay, yeah, we've just seen at last presentation that the renewable capacity has been increasing not only in Germany, but around the world. And there's many facets related to that. So first of all, just a selection, but merit order effect, for example, where renewable supply depresses the wholesale electricity price. Then there's firm behavior changing, which have now a diversified portfolio between conventional capacity, say a coal-fired power plant, and they have some intermittent renewable capacity. And then there's a balancing of forecast errors, which is most closely related to what I'm researching. And that is in this two-stage market setup, which we have, where most of the electricity at the apex spot market, about 80% of electricity sold is sold at the day ahead stage. But at this time, renewable in-feed is still very uncertain, right? It's still risky. So we only have to rely on forecasts, and these forecasts have been getting better and better, but they'll never be perfect, right? So there'll always be some risk that this day ahead projected amount of, let's say, wind energy that I have as a firm will be wrong. And so the question I'm asking is, do renewable firms react to risk in these weather predictions? And to motivate, consider a risk-averse firm with renewable capacity in a competitive market, right? And this firm, so this is just a very standard economic assumption, very simple. Did this firm react to both individual output risk? So really the risk I was talking about earlier, so how much electricity do I actually can sell in the end? And the aggregate price risk. So if I'm wrong with my forecast, and the risk is that at the intraday price, where I have to buy or sell the difference between what I sold and what I actually have, if this risk is high, then this firm will react to that. Yeah. And this literature is not very rich, at least in the energy economics area, but there's the seminal paper by Bessenbinder and Lemon from 2002 in the Journal of Finance. And what they do is they look at the price risk and how retailers, so basically the middleman between the wholesale market and end consumers, households, for example, how they react to price risk. And what they find is if the price risk is higher, they actually buy more in the day ahead market in order to ensure, or in order to hedge themselves against a very high price in the intraday market. And what I presume that renewable firms now do is that they hedge against the price risk by reducing output at the day ahead stage. So they want to hedge themselves against being wrong in the intraday market. And this withholding of renewable electricity will then increase the day ahead price via the merit order effect. So less renewable supply, ceteris paribus, leads to a higher wholesale electricity price. And then the day ahead price will contain a risk premium compared to the intraday price. And lots of renewable capacity, at least in Germany, and I think that's the case around the world as well, is that it's heavily subsidized. For example, we started out in Germany by feed-in tariffs, which made renewable firms basically independent. Their profits were independent of the price at the market. But now, in 2012, the law has changed, and now firms are actually, their profits are partly exposed to the day-ahead price or to the price at the market. And this is more the case for wind in Germany, but now this becomes, as subsidies are being phased out, this becomes a more relevant question. Okay, so consider this, just a quick illustration. Assume there are two regions, right? If we want to stick to the case of Germany, there's a windy north at the coast and a not windy south. And this also applies to solar. I just picked the windmills for illustration. And then there's this region up here, which is very large. They have a lot of capacity. There's many firms engaging. And this representative agent, she doesn't really know how much electricity she'll have to sell, right? And then there's this single wind farm somewhere else. It's not that big. And she also doesn't know how much electricity they have to sell. So in this case, output risk of this plant and all of these translates into price risk. And then there's the case of the low price impact, where the high region, the high price impact region or the high output region, she's quite certain. So she relies on the forecast and knows she's relatively certain that this will actually happen. And then in that case, output risk does not translate into price risk. And I don't really expect much of an impact on prices. And of course, there's two other cases as well, where she's uncertain, but she's certain, and both are certain. Right, now let's move to the data. I use hourly data for Germany, 2015 to 2018. And I have data on the day-ahead price and the intraday price. And I also have information on the realized renewable production and demand, as well as the forecast. So I have information on the two main market stages. At the same time, I also have information on the underlying wind speed and solar radiation. And this is derived from this meteorological model. It's called COSMO-D EPS. EPS stands for ensemble. I'll talk about that in a minute. And using this, I derive a measure for risk. So there's no public measure for risk. So if we consider the stock market, there's the volatility indices and whatever that which can give us a risk. And in this case, I at least have to derive it from data. And I use this weather prediction model, which is very detailed. Again, I said this model is an ensemble model, and it predicts for every square kilometer grid in Germany the day-ahead wind speed and solar radiation. And for every point in time, there's 20 different predictions, right? So I have brought an example here for region 23. I'll talk about the region on the next slide, but this is the region where I'm from, so I was particularly familiar with this. And on the left, you can see the case of lower risk. So every ensemble member, they're relatively similar in their predictions. So what this model does is they get input data and then they change assumptions. Okay, if let's say this cloud cover moves a little bit to the left, or there's a little bit higher temperature, right? And all of those uncertain cases, day ahead, they lead to a very similar outcome, in this case, wind speed. So in this case, we can say that the wind forecast is relatively low risky. On the other hand, there's hours where one forecast leads to, let's say, 16 meters per second, and the other ensemble member only leads to about 3 meters per second. So there's a significant difference among these ensemble members. And in this case, I would say the risk is higher. At the risk of that the point value of the forecast will not happen it's higher. Okay, let's talk about the regions. Region 23, I think it's up here. So it's also quite windy, and you can see that installed wind capacity and installed solar capacity as well is not homogeneous across the country, of course, right? We have this very high capacity regions in the north where we also have the amount of offshore capacity. Then in the less densely populated areas to the east, there's more wind farms. And in the non-windy south, there's less wind. So this, going back to this illustration, gives me some kind of region. So assume there's more of a high price impact region, and wind uncertainty here in Baden-Württemberg, for example, doesn't really matter that much for the price. And of course, the same is true for solar, especially here at the North Sea. We have about 20% of install capacity only in these three regions. And these regions, they represent the first 2 digits of the postal code. Yeah, this is just a way to aggregate data from a square kilometer grid, which would be too much to handle. Right, and this, let's say, clustering of capacities, this leads to different specifications of the explanatory variable of interest, right? So I have the capacity weighted average output risk, which is weights the, let's say, wind capacity by region. And then I also split it into high and low price impact regions. And I consider a price impact, a region to have a high price impact if its capacity exceeds the 90th percentile. Let me say this right now, this cutoff is, of course, subjectively chosen, but the qualitative results I will present you next, they're unaffected by this cutoff. So if I go down to 70 or if I go up to 95, for the qualitative result, it does not matter. And then I have a binary measure, which for those high price impact region which I defines a high output risk. And also here I use the 90th percentile. Okay, let's move on to the identification strategy I have. So I have the price premium as my dependent variable, which is again the difference between the day ahead price, which still has this incomplete information, I would say, and then the intraday price, where all the information is there, and that's the true price, so to say. And I have demand, which of course explains the price level. I have a bunch of covariates such as coal price or allowance prices. So those that determine the marginal cost of fossil fuel fired power plants. And now, most interestingly, I have my risk variables and my weather variables. And those risk variables, I presume, they have an impact on the amount of renewable electricity that is supplied. Yeah, if there's withholding due to higher risk, there's less renewables that are in the system. And so I control for the weather, my risk, renewable forecast errors, which of course drive the price difference. They put an additional buy or sell pressure on the system. And the goal of my my regression analysis is to assess the presence of this arrow here, right? So is and I assume this risk is exogenous to the premium, which I think is a very reasonable assumption, since this is only based on weather, if this arrow exists. So if the risk is higher, is the amount of renewable electricity supplied lower? And what I do is I run dynamically complete time series regressions. And what I do find in short is that these regression results, they do not support a direct price effect of renewable risk. So my hypothesis does not get any support from these results. And the main drivers of the price difference between the day-ahead price and the intraday price, there are the forecast errors. Right, so if I'm with my wind farm, I'm short of electricity, so I have sold more than I actually have. I have to buy the additional electricity from the market, and that drives the intraday price away from the day-ahead price. Okay, so this is evidence or not evidence, so to say, in actually there's no withholding in response to renewable risk. What I do next is I look at the actual supply curve, a day-ahead supply curve. And what we can see here is those gray dots. They are aggregated supply and demand bids from the German day-ahead auction. And unfortunately, that's all the information I get from them. So I don't know who actually gave that order or who actually gave that supply bid. So I don't know if it's from a power or if it's from a conventional power plant or it's from a wind farm in the south. I don't know. So what I have to do is I actually have to look at the slope or at the shape of the curve, right? And if I presume that if there's renewable withholding, ceteris paribus, the shape of the supply curve should change, right? There's less supply, and let's say renewables bid somewhere around here. This should change, or this should actually decrease. So what I do is I calculate, I fit this polynomial spline, this cubic spline. So at every point, I fit a third-degree polynomial to the curve, and the bandwidth is cross-validated in order to maximize out-of-sample prediction power or performance. And what I then do is I calculate the second derivative, which should always increase with renewable supply. No, sorry, it should decrease in the market clearing pound with renewable supply. So if the market clearing pound is point is somewhere here, and there's less renewable supply, it should move up somewhere here, right? And again, I run a time series regression on now my second derivative from all of these hours is my dependent variable. And again, I do not find any effect. So the main drivers of the curve of the curvature, the shape of the supply curve, essentially are the weather variables. So this path does exist, which is just pretty much evidence of the merit order effect we discussed before. Right. So again, at this point, there's no support for the hypothesis that renewable firms in Germany react to price risk or to output risk. Sorry. And this conclusion is actually based on a regression on the price premium and on the shape of the supply curve. And I explain this result because this as follows. And one possibility is that firms simply do not have access to this information. Right? I've talked to traders at companies, and of course they do some forecasts on their competitors' output and also renewables, and they have their own models. But based on this research, these models do not have or do not contain the renewable risk. And even if they were to include it, output risk could possibly not be considered to be relevant information, right? So they say, okay, we have some kind of costs in getting this information, and then we have a benefit of this information. And potentially, the expected benefits from this information, they do not exceed the costs of acquiring this knowledge, and therefore firms behave rationally inattentive. And yeah, I think that's it. Thank you for listening, and thank you for staying this long. And yeah, if you have any further question, please reach out.
Thank you, Philippe, for this original view on the effect of renewables on the electricity markets. So we have plenty of time for questions. So yes, Richard.
Oh, thanks. Interesting stuff. So thank you for that. And I was just thinking about that supply curve. Could you go back a couple of slides just to show one? Yes. So it looks as if this is based on what people are, is this the supply curve in a single hour, and that
Yes.
generators are expecting, this is probably based on what generators are expecting to be doing, because there's an awful lot of kit that doesn't want to be turned off, possibly because of what it wants to do the next hour.
That explains the negative bits.
Yeah.
Yes.
And so I was thinking, firstly, that if I'm a wind generator with a €10 subsidy, my bid is probably -10.
Right.
Because I don't. But then the amount that I bid is the sort of thing that you'd be controlling based on how risky it was. And then thinking about the curvature, would it be that if you had a very windy day, then fewer thermal plants would be scheduled, and that would mean that in terms of megawatts, the range between the maximum that group could give and the minimum they wanted to give before the bids got very negative would be a shorter range, because there'd be fewer plants already operating. Is that something that's consistent with the data you're getting?
Yes. Okay. So this is only like an illustration for 1 hour.
Yeah.
Of course, and you can see that the range on the x-axis it changes, of course.
Yeah.
Right. But very interestingly, I found the range does not really change as much as I expected. But what you can see is, of course, it just shifts, but depending on forecasted demand, but the range is relatively consistent with the theory, of course.
Right. Okay. So it's more likely to be sort of ±6 around the 42 gigs rather than ±1/7.
Yeah, essentially.
Okay.
And I control for these time rigidities, so to say, by including lags of the previous hour or previous hours, in order to model like also your fossil fuel bits that are relatively dependent on previous hour bits.
Okay, thanks. There've been a couple of very ancient papers now on people underbidding in the British market to avoid imbalance penalties. One was Bathurst and I think Strabak, probably in an engineering journal 18 years ago. And Chris Dent from Durham, I think, also did some stuff, although I forget how far he took it. And that again was quite a few years ago, because they've kept changing the rules and getting rid of the penalties eventually. But that might be worth having a look at.
No, you can see that there's we've also have some gaming evidence for between the day-ahead market and the imbalance market, which would be the market stage after the intraday market. But they also said, I mean, this would if that happens, I think that would affect the size of the effect if there were one, but potentially not the presence of it.
Yeah.
Right.
And also California, one of the Borenstein-Bushnell papers of ages ago was on persistent differences between day ahead and real-time markets, and whether the generators would, why the demand didn't move away to react. If the demand realized that some of the generators were preferring one market, why didn't the demand adjust? And they had some interesting comments there, so that might be worth having a look at.
Thank you.
Might be Borenstein, Bushnell, Wolak, but I can't quite remember, sorry.
Thanks, Richard, for this interesting debate. So we have still time for a few questions. Maybe Madeleine, do you have any question?
Yeah, actually, yeah, no, it goes. Yeah, actually, just one. Yeah, I'm not entirely sure, but you had this graph there about the output risks for the you had for this Hamburg region. I was wondering how far is this conditioning on yesterday's weather? So I'm wondering how large is the output risk, considering, I mean, how much does this change over days? I know what weather was like yesterday. How large is this risk actually? Yeah.
Okay, so within a day, so hour to hour, this is relatively significant autocorrelation or correlation over time. But consider it but that I did some tests on that, and that never exceeded, let's say, 10 to 15 hours, depending on where you looked. But if you consider the day ahead, auction at 1 a.m., I think it is, for starting 11 hours later, for delivery 11 hours to 35 hours later, there's not that much influence on that.
Okay.
But that's a great point, and that's also what again shows that the specification of the regression model, by making it dynamically complete, which means that you have to include lags of the outcome variable, is very important.
Okay, I see. Yeah, I thought that this could be maybe one explanation for what you mentioned in the end about this rational inattention.
Yeah.
Maybe it does not play so much a role, but I see, okay, it does. It's the day ahead market. Thanks.
Thank you.
Thanks, Madeleine. Another question maybe from the audience? Okay, maybe Philippe, just one comment. I'm not sure it is relevant, but I'm wondering if all the renewable producers are fully exposed to market risk. And what I have in mind, with the end of feed-in tariff, especially in Germany, maybe there is more and more power producer from renewable side of the sector that are selling the electricity not directly on the day-ahead market, but to aggregators. And in that case, it is the regulators, the aggregators that are responsible for selling the electricity on the day-ahead market and compensate for the difference in the intraday. So how this change in the way power producers sell electricity may impact your analysis?
So in Germany, the case was that when we had this fixed feed-in tariff, they sold it to the grid operators, and then the grid operators took care of selling it. But now they get a subsidy. So let's just say wind, and 95%, it's pretty much, the most significant portion of wind capacity in Germany. And now they directly sell at the market. But it's very possible.
They have just a premium up on the power price on the market, but they can choose to sell the electricity not on the market and not take the risk, but to sell it to aggregators.
They have the possibility of, let's say, over-the-counter marketing, right? Again, there's no data, unfortunately, on over-the-counter contracts, but I think that would only affect the size of the effect if there were one, not the presence, right? I don't expect that all of wind capacity.
Yeah, but for instance, in most of purchasing power agreements, the price of electricity is fixed.
Right.
At least for a short period, but it's not changed over the course of a day. So it's something that you could think to add in your game theory.
Yeah, I will do that. Thanks.
You're welcome. So thanks a lot to everyone again for your participation. It was really nice. Maybe Richard, you want to add something?
Yes, just thinking that again, it would depend on institutional detail. if you did sell your wind to an aggregator, would it then be the aggregator that is going to be doing the bidding into the wholesale market? And if the aggregator is a bigger firm and a more financially sophisticated firm than perhaps small wind generators, and forgive me, I forget how large the typical German wind firm is, but then a large aggregator might be more likely to do complex financial calculations than the wind. So that might actually increase the odds at something happening, even though it makes life safer for the wind farm itself.
But maybe there is some compensation effects. If this aggregator holds farms in the north and in the south, maybe it could compensate for the effect of having only one producer. I don't know, but it's an interesting question. So thanks again to everyone. I just remind you that tomorrow at 1 p.m. we'll have the award ceremony. So we will release the name of winners. Yes, Philippe, you want to say something?
I want to ask about this. Where's the link to that session? Because I wasn't able to find it earlier.
I don't know. I don't know myself where is the links. It was the next thing that I want to make just after this session, to ask where we connect to the session. So I will ask to the organizer that sent to all the participants the link to be sure that you can attend the session. So the time is 1 p.m. and we will reveal the name of winners of best student papers, and you should receive a mail in the coming hours, or the information will be updated on the program. Okay? Perfect. So thanks again to everyone. It was really nice to session host say that you can ask to Bassem, of course, and the mail of Bassem is in the chat room if you want to get this link. So thanks again to every participant. It was really nice to have both sessions, and see you tomorrow for the outcome of this huge presentation. Thanks again.
Thank you. Bye.
Thank you.
Thanks.
Bye.
Bye.